Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko, and we are going to be attempting to keep it down tonight. Daughter has a friend over, so they're like right there. Alright, so tonight I'm going to be working with... Let's turn that down a little bit, at least in my head. The Mathematics of Space Exploration by Merle H. Ahrendt. Once the property of Maple Grove High School, and can't actually read that one, but it's like Remus Point Central School or something like that. So we're gonna take a look at the beginning of this, and this is allegedly intended on being like a 1965 Roger Moore? No. I am looking much more like my namesake at the moment, because I have not gone and actually gotten my hair cut or my beard trimmed, so it's just like, it's just really big. But so welcome back, Matthew. And hopefully this will help me improve my Kerbal Space Program game, because it was not good. All right. Also, I believe my English accent probably needs a little bit of work. Sir Rogerman, no. Thank you for the vote of confidence, but no. I can never pull off a suit like that either. Okay. Merle H. Ahrendt was an educational programs officer at Headquarters for National Aeronautics and Space Administration, Washington, D.C. Prior to joining NASA in 1964, he served as Executive Secretary of the National Council of Teachers of Mathematics. I was a member for 12 years, and as a program analyst for the National Science Foundation. Mr. Ahrendt has taught mathematics in secondary schools in Indiana and was a chairman of mathematics and physics departments, Anderson College, Anderson, Indiana. He has been an instructor in the extension divisions of Johns Hopkins University, University of Maryland, and University of Virginia. He was a delegate to the White House Conference on Education in 1955 and served as national president of Sigma Zeta National Science and Mathematics Society, has held memberships in several professional educational organizations, and was a fellow of the American Association for the Advancement of Science. Original drawings by the Versatron Corporation. If anyone is interested in Looking this book up, the Library of Congress number is 65-23270. And, its Dewey number as of 1965 is 629.4A. Preface. The ambition to explore space and the attempt to develop the needed science and technology are far from new. Isaac Newton had discovered the basic physical principles and related mathematics of gravity and satellite behavior as early as 1687. Pioneering work with high-altitude rocket probes was done as early as 1920 by Dr. Robert H. Goddard. There's a name we know. In the United States, and Hermann Oberth in Germany. The first V-2 rocket was fired by Germany in 1942. Writers of science fiction have produced many volumes describing imaginary spaceships. As part of its contribution to the International Geophysical Year, the United States announced its Vanguard satellite program in 1955. The space age and the space race began in earnest when the Soviet Union orbited Sputnik 1 on 4th of October 1957. The National Aeronautics and Space Administration was born on October 1st, 1958. Since then, hundreds of satellites have been orbited. Lol. We're in the getting close to tens of thousands at this point, I'm pretty sure. Of satellites have been orbited. An extensive program for the manned exploration of the moon has been organized. And the exploration of the solar system and even deep space are already being planned. Oh, this is quite dated. Man has crossed the space frontier, and it is inconsistent with his nature to turn back. The result will be profound changes in our viewpoints and manner of living. The recent developments in the space age have special interest for teachers, students, and other persons interested in mathematics. The person who is gifted in mathematics finds the motivation in the logic, structure, and beauty of the subject. But many of us have more appreciation of mathematics if we know something of its practical applications. Authors of mathematical textbooks, especially on the secondary level, find it difficult to obtain meaningful and interesting applications. The mathematical study of the mundane problems of taxation, home ownership, and other social situations elicits little enthusiasm from students whose interests in these matters lie quite a few years in the future. Yet these applications are the ones most commonly offered. Applications of the use of algebra are especially hard to find, since algebra alone is rarely adequate to describe physical and technological phenomena. Defacing my own book. How dare I? The mathematics of space exploration is almost ideally suited to fill this need for meaningful, even exciting applications. Much of the basic mathematics with which the space scientist or engineer begins can be expressed with linear and quadratic equations like those found in secondary school textbooks. The study and use of these equations helps the reader to better understand space phenomena and gives him an appreciation of the power and mathematics to help us interpret the physical universe. When a person has expressed a relationship in the language of mathematics, they not only understand the relationship better, but are able to predict the way in which it will behave in every situation and in which it will arise. The careful reader of this book will receive new insights into both mathematics and space exploration. Let's reset our canvas. When a person has expressed a relationship in the language of mathematics, they not only understand the relationship better, I've already said that, haven't I? Yeah. The space age presents at least 3 compelling needs to educators. 1, the steadily growing importance of science and mathematics in our culture make it important that these subjects receive increased emphasis. So... Two, the scientific and manpower needs of our nation require that we be able to successfully challenge students who have the ability to contribute in these fields. And 3, the schools must produce citizens who are literate about the space age and its implications. And I would dare say that the modern edit here would be very small to move that apostrophe from the inside of nations to the outside of nations. Yep, we are keeping it rather jazzy tonight. We'll say, right? Like, if it came around with all the spooky stuff tonight, it would actually make sense, but... go figure, it hasn't done it yet. Perhaps this book will make a small contribution into meeting those needs. Contents. Page 7, we have an introduction, and then we get into motion, mass, weight, and gravity, measurements for the space age, the nature of space, launch vehicles, bodies in orbit, and flights in space. Afterward, there is a summary of equations and formulas, answers to space flights. These represent a body of work put together by Ahrendt and another number of other people, which are basically like just problems, but they are sometimes actually fairly significant. So we'll see as we go through. Tables, bibliography, and the index. Yeah, spooky jazz does need to be a genre. Hey Phobos, how's it going? Is that literally the same song? No, not the same song. Ever so slightly different. Yeah, we're doing alright over here. Having an interesting night. We got a late start tonight because had our kids go trick-or-treating. We had one of our neighbors and one of my daughter's friends who is sleeping over, so I'm trying to stay quiet or something. I don't know. Hopefully they'll just get used to my daughter's used to the sound of my voice, so she just kind of conks out, but hopefully her friend's okay too. And if anybody does not know Phobostream, she is a math content streamer and does a whole bunch of other really cool stuff on platforms, so head on over and check her out. And if anybody has any awesome things they've been up to lately, let me know. Because why not? Alright, introduction. Some of this is going to sound familiar for what we've been talking about in our group. Mathematics has always given a sense of excitement and satisfaction to those with interest in it. You got bad sleep? Oh, sorry, Matthew. Or you got to sleep bad. Either way. Playing with mathematics leads continually to the discovery of interesting and unexpected patterns and relationships. No doubt one of the reasons for the appeal of pure mathematics is that of its subject matter is unrestricted by the bounds of the physical world. The ideas of mathematics are abstractions. The pure mathematician is not restrained by the requirements of the physical utility. The dawn of the space age has also given those persons who have an acquaintance with it a deep sense of excitement. The certainty that the exploration of space lies in the years just ahead may well be considered the most exciting and challenging development in the history of human relationship with their physical environment. Man has already orbited the Earth. Space probes have been sent to the Moon, the planets, and the Sun. Again. Quite a ways back. Like, this is pre-Voyager, this is pre, everything. Just came off a good streak. Yeah, that's good. Yeah, we got back from Paris, and, I had pretty much 8 to 12 hours of sleep every day. It was great. Came back this morning, it was 6. Okay. How soon and how widely people will explore space will depend on how rapidly they are able to acquire the necessary knowledge and technology. We have already crossed the threshold of the space age. Our interests in space exploration are literally out of this world. Thus, from a philosophical viewpoint, it would seem logical that persons who are interested in mathematics would also find it easy to be interested in space. Both are fields of exploration and adventure. Both are challenging to persons who like to pioneer. From a physical viewpoint, the relationship of mathematics to the space age is even more intimate, since mathematics is the very lifeblood of a space age. Although the pure mathematician is not concerned with the application of their ideas to the physical world, the applied mathematician and engineer are deeply involved. The systems created by the mathematician have become the language and the instrumentality by which physical relationships are expressed and manipulated. An exact science is impossible without mathematics. In fact, a science becomes exact only when its subject matter becomes sufficiently precise to permit expression of its relationships in mathematical terms. The laws and principles which make space exploration possible are expressed in the language of mathematics. The representation of physical laws in mathematical language not only makes it possible for the engineer to understand and apply them, but enables them to discover and apply new relationships. The space scientist or engineer would have no means of operating with physical laws and principles if mathematics did not exist. Well, I think I may need to look that up just in case. Okay. I am wondering if this is another typo. The propose and organization of this book. I assume they mean purpose, and it just got typoed in there. But I suppose there is the possibility that propose could be a noun, much like primer or something like that. But if that is the case, I am unaware of it. My dictionary that I looked it up on says that's nobody does that. It's not a thing. This book is not in any sense a book of engineering mathematics. The actual mathematical computations required in the design and operation of space vehicles go far beyond the relatively simple formulas presented in this book. For example, the orbit of a satellite about a perfectly uniform, isolated Earth can be described with equations no more difficult than those studied in secondary school mathematics courses. However, in actual practice, such ideal orbits do not exist. No surprise here. Every orbit is perturbed by other factors, such as the varying density and non-spherical shape of the Earth, the gravitational pulls of other bodies, the pressure of radiation and solar wind, and the like. Thus, if we were to follow the exact path taken by a satellite and predict it with a high degree of accuracy, its location at some future time, computations by an electronic computer are required. Oh no, not an electronic computer. In constructing the outline for this book, two approaches were possible. The book could be structured about topics in mathematics or topics in space science. The latter approach seemed more satisfactory. Thus, the arrangement of the book gives it some continuity as an introduction to space science. The applications of mathematics in the space age overlap many fields in science. Space science. The writer has attempted to give enough background information about the space science topics involved that the uninformed reader can understand something of the nature and significance of each mathematical application. The author, being a mathematician, is not an authority in any of the many space science topics for which mathematical applications are discussed. My God, that's like me. I could write this book. However, the author has attempted to collect information from authoritative sources, and the background information in the book is believed to be correct. For more complete information about the many interesting facets of space science to which this book alludes, the reader may wish to read some other books in this series. Readers who have completed 2 or 3 years of mathematics in high school should be able to use this book with very little difficulty. Readers who find in the book certain topics in mathematics which are new to them will fill in their backgrounds of information by reading the standard textbooks. The basic purpose of this book is to present in simple form enough of the applications of mathematics in the space age to enable the layperson or student who has reasonable knowledge of mathematics to form an appreciation and understanding of the role of mathematics in the exploration of space. How to use this book? This book is liberally sprinkled with problems or exercises called space flights. It is hoped that the reader will attempt to take these flights. The solving of these problems will, 1, assure that the reader understands the principles that are discussed. And 2, help them to discover important new relationships. The person who skips these space flights will only get part of the information that they should receive. The author has attempted to make these problems not merely exercises in mathematics, but when possible, discussions of actual space problems. Not all of these space flights are easy. Some of them are tricky and will tax your ingenuity. If your background knowledge of mathematics has diminished, a brief review of necessary topics will pay dividends in helping you understand this book and increasing your knowledge of the mathematics in use in other areas. We hope that you will enjoy taking these flights. Remember that a good mathematician is not easily discouraged. This is something that you'll hear us discuss in our groups here on platform, is that like one of the best things that you can do for yourself is gain a sense of yep resilience. So understand that you're going to end up failing quite a lot in doing a lot of the individual problems that you come across, and in failing, there is a lot of value. One of the guys I follow on Twitter, I will not call it by that name. One of the guys I follow on Twitter, I think it's Mathowitz, Carl, recently put out a tweet that said that he was he unfortunately was under a bit of a time crunch with a particular student and was unable to meet with them on the scheduled day, so they had to push it back, which unfortunately meant a lot less time to study for the exam that was on Monday. And the parent called and was rather unhappy and said, look, the kid just failed the exam. And he said that this was probably the first time that he really asked the question of the parent and then naturally to the student indirectly. What exactly does it mean to fail to you? So that's also an interesting question that we have to discuss and try and discover for ourselves. It's like, what does it mean to fail in your opinion? Over the years, right, I have failed to produce an answer to quite a lot of the questions that have been asked. A number of the puzzles that we look at here, including like the Collatz conjecture and Riemann hypothesis and things like that. Like, there's no possible way for me to actually answer those particular questions. I just don't have the chops for it. But in exploring it with what understanding I do have, first of all, we do expand our knowledge and understanding of where we are versus where we end up. So that in itself is just valuable. Even if I know that I'm going to fail to produce an answer in the traditional sense, I would not be able to solve that particular problem, that particular mathematics. Being able to discuss it, being able to understand something more today than I did yesterday is success. And this is really what Ahrendt and pretty much every other math teacher in the history of math teachers will tell you, is that like if you are understanding more today than you did yesterday, you have succeeded. Even if you are failing by whatever other standards you're putting on yourself, or your teachers are forced to put it on you, or whatever else. So get out there and learn. Tables of squares and square roots will be found in the appendix. The use of these tables will enable the reader to solve quickly and accurately most of the problems involving roots and powers. Ooh. I have to break out one of these bad boys. Hopefully y'all know what these are. It's the wrong way around. No, it just smells like plastic. Brief table of natural logarithms is included for the solving and problems of Chapter 4 specifically. Occasional values will be needed in we needed which lie between those given values in the table. These in-between values can usually be found with sufficient accuracy using linear interpolation, found in Chapter 2. We may end up discussing a little bit of calculus while we're doing a bunch of these as well. Since numbers obtained by measurement always involve some error, one must be careful in using such approximate numbers not to accept answers which are more accurate than the data from which they are derived. Generally accepted rule is that one should retain in the answer no more significant digits than are found in the least accurate measurements in the data. Most of the measurements used in the space flights are correct to 3 significant digits only. Therefore, most of the answers given have accordingly been rounded to 3 significant digits. So we're going to actually discuss sig figs a little. I really hate having to worry about significant figures, but then again, you know, I'm mostly a theoretician, so yes, you literally have. It was 2 songs ago. Really, guys? Really? Alright, we are going to... This is the same group. Oh. 6 tracks, 16 minutes. Well, there you go. That's the problem. Man. I may be getting limited to quite a very small number. There's a lot that's been paywalled. Oh, pretzel. Oh, buddy. Yeah, they've like really hemmed this in and cut it down to almost nothing. That? Weird. We can listen to Heart Dance Records, which has 10 hours worth of music. That sounds more appropriate. Calm, dreamy, enigmatic electronics. Almost all of them. Oh, I also really hope this is not just all like AI music, because that would be really depressing. Yeah, I mean, since I don't have an actual subscription, they're gonna like really limit my stuff here. We'll see how that goes. Allegedly, 10 hours worth of music, so. The author sincerely hopes that this book will give you the excitement of both mathematics and of space. The large amount of reading required of the author to become acquainted with these applications was time-consuming, but it also was rewarding. It is hoped that the reader will share in these rewards. Mathematics, one of the oldest organized bodies of knowledge, joined hands with and makes possible the newest and most exciting venture in human history. History. Missing a letter. Our wish is that you will become aware of the challenge and the adventure of these fields. Alright, Chapter 1, Motion, Mass, Weight, and Gravity. The mathematics of linear motion. Many of the statements and ideas expressed in this book will be unintelligible to the reader unless they are acquainted with the certain laws of motion and with mathematical equations which express them. Since types of motion are discussed in detail in textbooks of elementary physics, we shall not attempt to give a rigorous or thorough development of these ideas. We shall limit ourselves to an informal discussion of them and illustrate their use with a number of numerical examples. Velocity, or speed, is a concept which is readily understood by most of us to mean simply distance traveled per unit of time. Not really. Although physicists usually make the technical distinction between velocity and speed, we shall use them as synonymous. Oof. If we're able to drive 120 miles in 3 hours in an automobile, we know that the average speed is going to be distance traveled divided by time taken. Expressed by the general equation, V sub A is equal to S over T, where S is going to be our displacement, or distance traveled. T is going to be time elapsed. And naturally, this is our velocity and parenthetical average. If a jet airplane travels 2,300 miles in 4 hours, this will end up being 575 miles per hour. We can, of course, apply the principles taught in elementary algebra and solve for s or t as needed. Hooray. When a body starts from rest, it must gain speed for a while to reach its desired velocity. A change in velocity is called an acceleration. Acceleration may be positive or negative. A negative acceleration, or slowing down, is usually called a deceleration. If A is the acceleration and v1, v2 are initial and terminal velocities respectively, the acceleration produced during a time t is expressed by the given formula. With a slight modification. So we know that acceleration is a change in velocity. We're probably going to also use per unit time in order to discuss it. And what we're saying here is we could take the average acceleration, really. By doing exactly the same thing we did with velocity compared to position. So we're going to say that we're going to take our second velocity, subtract our first velocity, and then divide by the total time taken. Well, we've done all sorts of stuff like this in our calculus class when we were talking about a number of, we weren't doing the class here, but anybody who's taken a calculus class, you've seen this before. It works with much the same principles. And actually, I'm gonna mark that as we're also going to separate our times into those two positions. So it doesn't have to just be the distance between those two times, it can be the actual literal numbers or measurements for those times. Again, we've done this all the time in, even basic algebra, but also when we were talking about average velocity, when we start comparing average velocity to instantaneous velocity in Calculus 1. Thus, if an airplane flying at a speed of 100 miles an hour increased its speed to 300 miles an hour over 5 minutes, then again, what we'd be looking at for in this particular case is what is the net change in the velocity. 300 minus 100 is going to be 200 over a 5-minute period. And here we have miles per hour for both of those. Going to get 200 over 5, or 40 miles per hour per minute. And naturally, from a resting start, this is going to yield that we would start from 0 miles per hour at v1, and so our acceleration would end up being, nope, our v2, you know what, fine. Our acceleration would be equal to v2 divided by t, or v2 would be equal to a times t. Equation 2 here, which is this one. Will be used many times through the book. For example, if an airplane gains speed at a rate of 80 miles per hour per minute for 5 minutes, then the velocity attained at the end of the period of acceleration is 80 times 5, or 400 miles per hour. If we wish to find the distance that a body moving with a constant velocity will travel in a over a given interval of time, we use the equation obtained by solving equation 1, v sub a equal to, that's the average velocity that we were talking about up here. That's equation 1. By solving equation 1, for S. So if we were to solve for S, that would cause our t to come over to the other side, just like we did before. And our S would be equal to v sub a times t. Oftentimes, these would be labeled as s of t, or even x of t. Here being our distance traveled, the displacement that we're going to displacement that we will be at after a given amount of time. And again here, most of the time this is going to be v of t is equal to a times t. Can't always guarantee it, but most of the time that's what we see. And let us consider again the case in which a body starts from rest and travels with a constant acceleration, that is, with a steadily increasing speed until it reaches a terminal velocity v. The average velocity will therefore be 0 plus v divided by 2. Goodness. No, okay, that's fine. That's going to be equation 3. right? So this is our literal average. This was not actually going to be specifically over a 2-second period, despite that being fairly common practice here. They're merely saying that this is going to be the average velocity, where in this case we're just taking our starting velocity, our ending velocity, and summing them up and dividing by 2. Mostly because the rate at which velocity is increasing is linear. So therefore, because the rate, because the speed is linearly increasing, then we're going to have a linear average. It's a constant rate of change in velocity. And so that's 1/2 v. But then we already talked about this here, equation 2, being what we get for v. So this means that we end up with 1/2 at. So from a more algebraic perspective, this is how you might be able to figure out that our yeah, no, that's fine. Sorry, I got lost there for a sec. 1/2 v is equal to 1/2 at, which means that v is equal to at, and also and also we can take equation 3 and say that s is going to be equal to v sub a times t, and we know that v sub a there were 2 different things we were going for here. V equals at, and also this one here, s is going to be equal to v sub a, which is 1/2 at times t. So s is equal to 1/2 a t squared. Yeah. Like, I have 2, but it's been a long time. Right, and then again, we can look at this from different perspectives to see different pieces of the same sorts of formulas. So here this said, let's see, this is going to be equation 4. Equals at technically was, right, equation 2 from above. Alright, ads starting at about 30 seconds. I'm gonna go downstairs, refill my water. Should be back fast enough. And I think I got another hashtag not sponsored drink, so. is. T is equal to V over A is from equation 2. We just rearrange it. And plug it into equation 4. That will get us I'll have to wait for 3 minutes. All right, what are we doing tonight? You want to see some stick work with a Screama, or do you want to see karate form? This is before I take a drink of this. Tonight is hashtag not sponsored by Botanicalist Gin and Tonic IPA from Magic Rock Brewing and Masons of Yorkshire. Think magic. Drink magic. I like the can art. It's pretty nice. Without further input, I'll probably do a little bit of stick work because we were supposed to go to a Screama tonight, but, you know, hanging out with the kids instead. Go figure. That's one of the things that happens when you've got Halloween. So, hope everybody's having a nice spooky night. And yeah, it turns out today wasn't very spooky for me. There's no real Halloween costumes. Might have to work on that for next year. I've seen some really good ones. Casticlism. Let's see. Both of the Maggies, actually. So, Casticlism and Maisie have been doing really well with theirs. Saw a good one with... Whoops. Saw a few good ones on a few different channels. I can't think of any right now. Come on now. Yeah, losing it. Alright, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Alright. Let's see. Last time we were doing this, going forward, back, forward, back, forward, back, forward, back. If I accidentally slip with one of these, like, my whole setup's dead. These are 500 grams each. So, they're pretty good. They're also 26 inches long. So they get going at a pretty good clip. If I end up hitting myself with this, like... okay, it's far enough away from my feet. I'm not gonna, like, break my foot. Let's see, what else do we do? We did 1, 2, 3, 4, 5. 1, 2. Yeah, right. 1, 2, 1, 2, 3, 4, 5. 1, 2. Nope, that's the wrong one. So yeah, the thing we were working on 2 weeks ago when I last went to class, because last week we were at last week we were in Paris, and today, right, was Halloween, so we're hanging out with the kids instead. These are... Oh, you can't even see what I'm doing half of the time over there. That's great. So these are Eskrima sticks, sometimes known as Kali, K-A-L-I. They are a weapon of the club variety, although when they're used for real in the Philippines, they are machetes. So, this is one of those where, like, the less I know about it, the probably saner I will be. But yeah, we've been taught quite a few horrifying things about, like, you know, the origins of Eskrima, and like they're not so much anymore, but there used to be like duels to the death with Eskrima masters, and like it's just ridiculous some of the things we've heard about. But our instructor is from the UK, and learned from a guy who regularly goes to the Philippines to get like updated on the newest Eskrima stuff. But yeah, it's really scary. Yes, these are exercise equipment, obviously. But I mean, like, literally anything is an improvised weapon if you use it improperly, asterisk. So you do have to, generally speaking, be careful. I cannot carry these openly anywhere, because police will just be like, what's all this, sonny? Yeah, they would not be happy with me. Similar to my lockpicking kit, I have a pretty good piece of kit somewhere in the house, and like if I have it outside of the house for any reason, it doesn't even matter. They'll just be like, you, sir, are planning on committing a robbery, so you're under arrest. So I do not take lockpicks anywhere. Whereas in the United States, in Maryland specifically, you could have a lockpick on you as long as you are not also committing another crime. Because as soon as you commit another crime, they also tag on intent to use lockpicks to burgle. Anyway, yeah, so the typical motion for us, it's called Sticks to Heaven. We'll start from one side, and we take a swipe at totally not somebody's head, and then bring it back, and then pop out underneath at totally not somebody's waist, and then the two sticks swap position, and then this comes down to approximately the hip to be rechambered for the next motion. And then we do the same, so head, back to shoulder, low strike, swap, and resheath or rechamber. So again, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And when you get doing it with a partner, your motions exactly mirror each other, so you can actually hit sticks here, rebound, hit, swap, hit, and rechamber. So you get clack, 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 and it gets really loud. I've been thinking I probably need to bring earplugs because it's quite loud when you're in a small space. And it turns out that these, A, are probably too heavy and might be doing some harm in terms of my form. And these, which are 28 inches and only 250 grams, are actually shredding the rattan sticks of my partners. So I should not use these in partner work. So they're polycarbonate. They don't do anything. Like, you smack these together against each other or against wood like, 1,000 times, nothing's going to happen. But the rattan that my partners are using is just splintered from about here to here. Like that whole last section is just all starting to delaminate. It's pretty bad. So I was like, okay, I'm just going to use the sticks that our instructor has from now on, because, again, these are just too heavy, and those are just too punishing. They don't have any give, being made entirely of heavy plastic. Oh, can you actually get some brews? Yes, definitely. So I have not in quite a while, but we did have a couple of times where we were actually, like, we had we were holding the sticks, and your job is to hold the stick like this, and that is it. And you movements that we had, which was like coming from open. So open stance on this side, smack over here, change, like to do a one this way and then one that way. You do one this way and then, or do one this way, then come that way. There's all sorts of combinations that you can get. It's really cool. And then I generally like to train both sides. Over the top. That's another fun one. But the one that was most punishing was, you're standing there like this, you're just bracing for a hit, and the person comes in and they go 1, 2. So it's above your head. You do a fan block, which going this way will knock the stick that way. And generally you're holding it, so it's like, goes about that far. And then you come back the other way, and then it goes like that. So you go like 1, 2, and then the next move is to sink in at the waist and drop this in a comma shape to go whack like that. And the point is to bring the second stick directly down on the person's hand. So your job is to go 1, 2, and then hit the stick somewhere about here and just directly drop that stick into the person's other hand. We're wearing, like I said, gauntlets, essentially, that are meant for punching. They're meant for hitting other people. They're not meant to block like this constantly against your hand. And so it was like, a 1-hour lesson where that's all we were doing. And just like my hands in this whole area up here were just yellow for like 3 days. It really was not pleasant. Well, thank you for indulging me. Yeah, so if you're actually going to be interested in doing eskrima, I highly recommend doing it as a second martial art. I have a first degree brown belt in Tang Soo Do Karate, and the other two gentlemen that I am working with, who are also students at this eskrima studio, are black belts in Tetsudo and Shotokan, I think. So, like, we've all got a karate background, but they're also very different styles of karate. It's kind of interesting. I don't know. I feel like oh, and the guy who does Tetsudo is also deaf, so it makes it really nice that he doesn't have to worry about like all of the noise that's in the room. It's, oh man, it is so loud. I think I put on the decibel dosimeter just to see like how bad it was, and it was I can't remember if it was over 80% of a 90 plus decibel dose, and like 60% above 100 decibel. I mean, it was loud, and that was also a hot week where like it was really warm, and he had to close the windows up top because the neighbors would complain of the noise. Or rather, he doesn't want to risk it. But hey, if anybody wants to ask anything about martial arts or anything like that, feel free, because I do love telling stories occasionally. Alright, so we're taking our S equation from number 4, and we're going to plug in t as a function of our velocity and acceleration. So we end up with s is equal to 1/2 a parentheses v over a squared. So s is equal to 1/2 a times v squared over a squared. So this is s is equal to 1/2. We got 1a up top and 2a's down at the bottom, so we divide that out. And this is going to be v. I might as well extend that. So 1 times v divided by 2a is equal to s, or we could also say that v is equal to 2a s. Oh, v squared. Alright, that is equation 6. Or did I miss one? Lol. S equals v squared over 2a. Okay. Yeah, so Kali sticks are classified as a club weapon if they're ever used not appropriately, or ever used to actually hit someone. They are considered a club weapon. So don't do that. I was like, man, I could get like a, actual like Deadpool outfit and slide those in X style in the back, but no, that's too dangerous. Run the risk of having some police be like, what are you doing? Like I said, what's all this in, Sonny? The difference between velocity and acceleration should be clear to all persons who have ever driven in an automobile. When the automobile starts from rest, we depress the accelerator pedal to produce a force sufficiently large to move the automobile. It gains speed steadily until it reaches cruising speed. We then ease up on the accelerator pedal and give the motor only enough power to keep the car moving at a constant speed by overcoming various sources of friction, such as friction of the tires on the road, of the internal machinery, and of the automobile with the air. If no force were needed to overcome the friction, the remainder of the trip would be free, without the expenditure of any additional power. This is precisely what happens to a craft in space when it moves under the influence of gravity. Right, and also, kind of important, gravity is not by itself a force. Not a controversial statement. Despite the fact that everybody wants to say, what? After sufficient force has been applied to place it in an orbit far enough above the atmosphere so that friction with the air is no longer present, the aircraft will continue indefinitely in a gravitational orbit without expenditure of further power. No motion is possible, of course, unless a force acts upon a body to produce it. So everybody at rest will remain at rest unless acted upon by an outside force. The acceleration produced by a force is proportional to that force. Acceleration is proportional to the force, relationship expressed by Newton in the second law. F equals m times a. Wholly necessary. I actually just watched a video by Veritasium this morning, which was on the relationship of Newton's second law to the brachistochrone problem, which was Bernoulli's contribution to, physics, but basically, there was a French mathematician, well, natural philosopher, by the name of Maupery. I have to look it up now. scientist. Maupertuis. Pierre-Louis Moreau de Maupertuis. French mathematician, philosopher, and man of letters. Became director of Académie des Sciences. This guy absolutely badass right here. This is a great picture. I thought for half a second that his rear hand was not upon the globe, but rather like this. I was like, absolutely yes. Like he was dancing. His front hand was coming across his body like that. I totally thought that his backhand was like doing something with a dance. Anyway. Obviously I've had too much of this already. No. He came up with an idea known as the principle of least action, which, like, almost everybody was just like, absolutely not. You're making that shit up. There's no chance, 0 chance that is true. You know, Derek from Veritasium said, like, a quarter of the people were just like, you're making this up. Another half of them were like, or another quarter of them were like, you plagiarized that. And half of his other, you know, colleagues, friends, whatever, just ignored it completely and were like, no, this isn't even science. And then Leonhard Euler came along and said, no, he's actually 100% right. And by the way, all we need to do to prove it is, like, alter a couple of preconceived notions, a couple of the assumptions that we're making, and look, it works perfectly. And everybody's like, oh, yay, Euler. And Maupertuis like, I mean... So Euler gave him credit. This is something that I think it was Steven Strogatz said in that interview with Derek, where he was just like, Euler seems like a kind of stand-up guy, not just like a really good mathematician, but he was also kind of nice, which a lot of the other mathematicians at the time were kind of capricious and nasty to each other. So he gave credit where credit was due. Told everybody that Maupertuis was 100% correct. Just didn't quite have the the rigor that everybody wanted him to have. Okay, so we can use any number of individual forces and accelerations. If it ends up being that there are 2 distinct different ones, we could also check their ratio with each other. So like F1 equals MA1 and F2 equals MA2. If we were to check the ratio F1 to F2, that would be equal to yeah, right. A1 to A2. So these things would be inversely proportional to each other. We could say that they, in both cases, right, equal M. That's not right. Nope, never mind. No, they're not equal to m. It would only be equal to m if it was f over a. Here we're just saying that the m's will divide out when we divide each of the left and rights with each other. If we could determine the acceleration a produced by force F, we can calculate the above proportion, the acceleration produced by a different force, F. One way in which to determine the acceleration produced by a force is to let the body fall and then measure the acceleration. Reasonable. Then the force is the weight of the object, and the acceleration experienced by the falling body is g, the acceleration of gravity. And so we could let F2 be equal to the weight of the object. And A2 be equal to G. And so with that, we end up with F1 over W is equal to A1 over G. Or that we have F1 is equal to A1 W over G. Or W over G times A, in which F is the force in pounds, W is weight in pounds, G is the acceleration in gravity in feet per second squared, A is the acceleration produced in feet per second squared. Careful measurements show that the average value of G at the surface of the Earth is very approximately 32.2 feet per second squared, or 9.81 meters per second squared, depending on what units we're using. It would seem to be intuitively expected that the gravitational pull of the Earth upon a freely falling body would produce an acceleration. The Earth gives a steady pull, and the falling body begins each new second of fall with the velocity reached during the preceding second. Thus, the body falls ever faster. The above equations and motion enable us to understand many of the physical phenomena related to motion or traveling and solve many interesting problems. Citation needed. Equation 8. Suppose a person weighing 150 pounds is riding upward in an elevator. The elevator starts from rest and has an upward acceleration of 3 feet per second squared. We're going to call it positive. The period of acceleration lasts for 3 seconds. At the end of this time, the elevator will have attained cruising velocity. What is that velocity? And what is the force exerted on that person? So our cruising velocity, let's go with 1, 2 like that. Our cruising velocity, given that we are accelerating at a rate of 3 feet per second squared, 3 feet per second every second, over the course of 3 seconds, this is just going to be v equals a times t, which is going to be equal to 3 feet per second squared times 3 seconds, which is going to be 9 feet per second. 2, what is the force exerted on that person? Riding upwards in an elevator, again, this is going to be F equals m times a. Okay, so the force of the person in the first place, the weight they have, is 150 pounds, which means that their mass is unknown, and the acceleration is 32 feet per second squared. This is pounds. M equals 150 over 32. Alright, this is pounds per feet per second squared. That's great. Okay, 150 over 32 is going to be 75 over 16. Or potentially we could leave it as 150 over 32, because get the feeling some of this may come in useful. We'll see. Okay, that is going to go in to our m on the next one. 75 over 16 times our a, which is going to be 3 feet per second squared. This is feet per second squared, so those will divide out nicely, and we'll be left with pounds. And that'll be our force that we have here. So, yeah, that'll be fine. 375 is 225 divided by 16, and this is in pounds. So our F is going to be approximately, that is going to be 1, and 6 left over, 65 on 16 is going to be 4.1/16. 0625, I think. In fact, that's going to be not approximately. It's going to be exactly that. Pounds. In theory. Yep, cool. Alright, and if we're being technical about this, 150 pounds is only 2 significant figures. Right, we don't have any information about where this number is cut off. So this could be like 148 pounds or something like that, but we're just rounding it to 150. So realistically, because of this, we only have 2 significant figures, and so this is going to be 14 pounds. We just call it good enough. Right, you do have to watch your precision, as much as I don't want to care about it. Alright, what do we get? Right, so what they did was they said, let's not even worry about the F equals MA bit, let's not worry about M. I wanted to worry about the mass because, you know, I'm just a completionist, but we could use equation 8 and say that we're just going to plug in these individual values. F was the unknown, A was 3, W was 150, and G was 32. So it's all the same stuff. It's just plugged in efficiently. Right. F equals A times W over G, which was, again, 3 times, nope, 150 over 32. Ooh, I forgot that one. 0.2. 16.1. Oops. 225 over 16.1. Uh, 13.975 with some change. Alright, but by significant figures, again, we only want 2, and then we need to round based on the next number. So 14 pounds being 2 significant figures without without putting a decimal point down or anything like that. We don't know how accurate it is. Just say, again, 14 is close enough. Right, so what would a scale read? If they were, sorry, accelerating upward, then that would also be pushing downward against a scale. So they have their weight of 150 pounds, and then also this particular case, the vectors are going to be added together. This is 164 pounds. When accelerating at cruising speed. Okay. This also gives us another bit. So, for instance, a jet airliner. The Convair 880 has a maximum takeoff weight of 184,500 pounds. Each turbine engine has a maximum thrust of 11,200 pounds. So the force available to push the airplane forward is going to be 11,200 pounds times the number of turbines that the plane has. In this case, the Convair 880 is a 4-turbine plane. So this is going to be 4 times. You don't need to see the mess over there. It's fine. 44,800 pounds. What is the max acceleration of this aircraft if it's being pushed forward at maximum weight? So the maximum takeoff weight is 184,500 pounds. We know that it has a thrust force of 44,800 pounds. And so we want to know what is the, one more time, what is the acceleration of this particular aircraft when it is fully loaded. Now A is going to be equal to, we can multiply our W over G the other way around, G over W times F. Right, which is going to be 32.2 over 184,500 multiplied by the thrust force of 44,800. Right. What do we get? Let's see, we drop 100 off of each of those, so 448 times 32.2 divided by 1,845. Or you just multiply all the numbers together. And we get a total forward acceleration of 7.81875 feet per second squared. Okay. And again, in this case, best we could do was 3. Hey, Brandon. Yeah, I'd even say the majority. Ayo. I don't have anywhere near enough statistics, expertise, or anything else in order to honestly call this. I mean, just based on personal, gut feeling or whatever, this is going to be a massive division, but like Arnold Schwarzenegger put out a very interesting tweet the other day. So I don't think it's 50-50. I think it's going to be closer to 60-40 in favor of Harris, but there's going to be a lot of voter suppression. There's going to be a lot of attempts to just not count people's ballots and all sorts of cool stuff. And I don't mean cool as in like awesome. Because they have money to make. Okay, so we've got 3 significant figures here, which does mean that probably this is going to be a 7.82 feet per second squared. I mean, maybe they're counting on misogyny. I don't know. I don't have a good reason why this only has 2 significant figures in the book. Anyway, I think we should have 3 based on all the information that we were given above. 3 is the minimum number of significant figures. If you want to argue that 4 only has 1 significant figure, I'm going to tell you that there are distinctly 4 engines on this plane. Okay, we'll take a 3-minute break here, and ads will run here. And thanks for sticking around, and see you in a minute. 3 minutes. That's cool. All right, welcome back, everybody. Um, yes, we all have the treat corn emote today, so show that off in your favorite trick or treat locations. It's just amusing. So we came, or we went to Walt Disney Studios. No, well, yeah. Disney Studios in Paris. So Walt Disney World Paris and all that. And we went to an animation session. So the gentleman who was there was a Walt Disney animator, trained in being able to teach other people how to draw a particular character and just like sketch out, okay, here's what you do when you want to make this person. My spouse and I both did Mickey back in 2008, 2010, something like that. Whenever it was that we went to Disney just by ourselves. And this time around, because it was Halloween, or, approximately Halloween, they had us do Jack Skellington. So this is, I just wanted to show off. I've hidden all of our names, but yeah, this is our 8-year-old son's artwork. I must say, like, he's 8. This shows some actual, like, promise. He's also extremely interested in drawing and doing cartoons and stuff like that, so I get the feeling that he's gonna probably do something like this for profession, not necessarily literal cartoons, but something artsy. So I think he did quite well. I was congratulating him for quite a while. He was just like, dude, cool it. Our 11-year-old, who is also quite arty herself. So I like the... now we were all told to draw all of the individual parts that make up Jack Skellington. But, she's got quite an eye for all of the individual parts that make up this whole thing, and she's really good at following directions. If I'm honest. But she's got a handle on kind of like the gentle sketching out of a larger picture, whereas like our son kind of, I don't know, I think on the bow tie part, he kind of did like a one and done. You notice that like a lot of this stuff over here is just a single draw, a single line. And I don't know if that just comes down to impatience or whatever, but like he did a lot of one and done stuff. Not so much the circle of Jack's head, but nonetheless. Again, whereas our daughter was very much like probably the both of us, and ended up drawing in these lines here quite a few times before like laying down one much thicker line. My spouse did also a very nice job. So again, doing a good job with getting the lines going in a couple of times. to really lay down like a baseline. Like this is where we're putting this particular line. And then mine, I sort of cheated. After everybody put in like the individual, after everybody like laid down kind of thicker lines, I went in with my pen. So I've got a couple of zebra, hashtag not sponsored, 402 F402 pens that have a 0.7 millimeter ink cartridge on them. And like I went over a number of these lines just to get them like really solid and drawn in a little bit thicker. So you can tell, especially like on the cravat, his neck, around the edge, somewhat around his head, but mostly around the eyeballs. Like I darken those up using actual pen and ink, which pretty much nobody else did. Nobody else had time to do. So it looks a little bit cleaner, and it looks a little bit more solidly drawn in. But like I said, I kind of cheated on that and ended up using pen and ink rather than just relying on darkened pencil. Honestly, could probably have done with a Sharpie and like, done a single draw through of like all the outlines in Sharpie. A little thicker and a little bit less, I don't know, a little bit less of the 0.7 millimeter. Like doing something a bit bigger would have been better. But yeah, that's how we spent our last morning, I think, while we were there. Then most of the day was spent walking. They wanted to go from one park to the other, and we're just like, no, we're staying in one park until we're done with that park. So, what else do you want to get done in here? And so we did the Iron Man ride in the Avengers Plaza, which was really good. It's a launch start roller coaster, so they do a maglev start. It gets you from 0 to 70 in about 2 seconds. So after 1 minute, it's 60 seconds exactly. We can, put in whatever 0.0000 we want in there. After 60 seconds, we end up with a velocity of 469.2 feet per second, and then we can convert that to miles per hour if we really feel like it. It's somewhere close to 320 miles per hour. I'm not even going to do the conversion on that one, but like if you wanted to, right, that'd be 469.2 feet per second multiplied by this is going to be feet per mile. It's 5280 times seconds per hour. 1 hour is 3600. So multiply that 469.2 by 3600 over 5280. All right, you know what? It's not that bad. Times 3600 divided by 5280 is equal to, yeah, 319.9. So 320 miles per hour. Given three significant figures, we could even drop the point right there, 320 point. If we really felt like it. The plane does not perform in a fashion as spectacular as this because a significant part of the thrust or moving force must be used to overcome friction, and therefore the acceleration is diminished. Woo! Alright, space flights. Cool. -1. An automobile slows down gradually from 50 miles per hour to 20 miles per hour over a period of 10 seconds. What is the rate of deceleration in miles per hour per second? What about in feet per second, or feet per second squared? Okay, so if we go for 50 miles an hour to 20 miles per hour, this is going to be 20 minus 50 divided by 10 seconds is going to get us -3 miles per hour per second. So the deceleration is 3 miles per hour per second, or our acceleration is going to be a -3 miles per hour per second. If we want to get feet per second, or feet per second squared, then we're going to take our pretty much the same thing we had on the last one, where we're going to take that -3. This is miles per hour per second. So this is actually like hour seconds. Right, because again, we want it to be seconds squared eventually. We're going to have to multiply by, we want miles to be dropped out, and 5280 to be our feet. Then we're going to want to multiply by hours up top, and 3600 seconds on the bottom. So this is a nice, easy one, comparatively. We get 3 times 5280 divided by 3600. We're going to get 4.4, and it is in the negative direction. This is feet per second squared. Alright, 1-2. An automobile traveling 45 miles an hour comes to a complete stop. Over a period of 10 seconds. After the initial braking. Find the deceleration in feet per second squared. Find the distance required for stopping. Okay, so again, we got 1 and we got 2. For number 1, our rate of deceleration is going to be, if we got 45 miles per hour, this is 0 minus 45 over 10.
Rating party!
It's a rating party. Thank you, everybody, from Don Does Math. Hey, how's it going, Don? What are you up to these days? I had you sort of over on the other window, but I didn't notice exactly what it was. We are doing some mathematics of space exploration by Ahrendt. Not Arndt. Ahrendt. Muriel H. Ahrendt, who was a member of NASA and various governmental positions, a leading administrator in charge of National Council for Teachers of Mathematics, or NCTM. And this was doing some stuff way back in... This book was published in 1965, so, like... There's some assumptions. Andres, what emote? Dare I ask? Yeah, and I can't even remember where this one came from. It must have been in the group of stuff that came from that. We also lost our music. Hang on. Where's our music? You punks. Oh. Anyway. Oh, be shocked. Yep. I do rather like that one. That was like the best art I have done. There we go. We were discussing earlier that Pretzel seems to have gone mostly behind a paywall. So I am rather disappointed. Which is unfortunate, but whatever. It'll work. Yes, and I am looking rather Obi-esque this week, because I have not cut my hair or shaved my beard, or trimmed my beard very shortly. Oh, yeah, you were looking a little bit up. Yep, that'd do it. Sorry, it only printed it out as words, so that's what got me confused there for a second. So anyway, how's everybody doing from downstream? Seems like y'all were having fun. Yeah, so I think I got this book in the stack of books that I got from the University of Maryland professor, retired, whose son was like cleaning out his attic, and there were 14 boxes worth of math books. Granted, not all of them were math, but it was like the books that he had in his office when he was at the University of Maryland. I was just like, I wasn't expecting this many. So we got this. We got, yep, the problems in differential equations, numerical solutions of ordinary and partial differential equations, which of course differential equations is like my field. So spent most of my time looking into those and like keeping most of them. A bunch of them I have gotten rid of. I've handed them off to various other places, and let somebody else. Yep, no problem, chaotic dude. We're doing The Mathematics of Space Exploration by Merle H. Ahrendt. And like I said, he was somebody who was active in National Council for Teachers of Mathematics, or NCTM. He was national president of Sigma Zeta, National Science and Mathematics Society, and held several professional educational organizations. Was also a fellow of the American Association for Advancement of Science and a member of NASA. So, like, yeah, you could probably write a book on space exploration. And how do you use math in space exploration? Now, currently, we are doing what are called the space flights, which are basically just the problems that come out of the first chapter of the book, which is not particularly difficult. If you've ever done any sort of mathematics at, like, Algebra 1, then that's where we are. Yeah, so this is like the super easy stuff. Motion, mass, weight, and gravity. Looks like the next section is going to be on the mathematics of circular motion, which includes centripetal force, force due to gravity, and how do we deal with 0 divided by 0, the indeterminate forms. So, like, that's kind of cool. This is meant to be like a high school level treatise from 1965. So, granted, a lot of things have changed. Yeah, there was a good bit in the introduction that was like, humankind has already orbited the Earth. Space probes have been sent to the moon and planets and the sun. That's it. I was like, oh, that's how far we are. It kind of forgot for a minute that you know, we'd only sent people to the moon in 1969. People have orbited the moon as of, like, you know, 1968, but in fact, I don't even know what the proper timeline is for that. Hang on, let's just double check that real quick. Right, list of Apollo missions with their Saturn 1B, launch escape system test, Saturn 5. There we go. Woo. Manned flight. Complete mission except for final descent 2. Right, so that was Apollo 10. Apollo 9. Apollo 8 was the first crewed spacecraft to leave Earth's gravitational field, December 1968. So yeah. Pretzel is the music free to use music platform that I have been using for quite a long time. I am getting slightly disillusioned with it because we found that today it was on a, so like I had selected a lo-fi station which had, I don't know, 300 hours of music or something ridiculous like that, and I found out today that we had been automatically moved to a station that had approximately 36 minutes worth of music. I was like, so everything got paywalled, did it? And it literally played 2 songs, or the same song, 5 minutes apart. So I said, yeah, we're not doing that anymore. It was all music by the same one person, or one group. So we shifted to a 10 hours station, which is everybody that is on this particular label. So this is, which one's this? Heart Dance Records. And I was griping to myself that I really, really hope this isn't like an AI created music station, but sounds like it's at least halfway decent at the moment. Okay, we got 4.5 miles per hour per second, and again we're going to multiply by miles. We need feet, so this is going to be 5280 divided by 3600. Again, we're trying to convert 5280 is going to be miles to feet, and 3600 is going to be hours to seconds. So 4.5 times 5280 over 3600 is going to be 6.6. So this is going to be a negative 6.6 feet per second squared as an acceleration for, what is this? Car? I think it was a car, yeah. Going from 45 miles an hour to 0 miles an hour in 10 seconds. So that's going to be our rate of deceleration in feet per second squared. how far is it going to travel before stopping? So here we end up having s is equal to a times t squared. Right. Technically. We do want. So I know how to solve this super easily, right? We just add a second term, which is going to be based on the velocity. So this is going to be our v0t. Not a problem. We know how to do this. But the reason why I'm kind of griping about this is that I want to use just one thing that is one equation with one term. And so this ends up being, I think we can just use s equals at squared if we set 45 equal to our, that's miles an hour, never mind. Why am I doing that? No. What was I doing? Right? Okay, no, this is fine. So we'll just do, this was a 4.5 miles per hour per second times the number of seconds it takes is 10 squared. All right, and this is, okay, this is fine, because this is the reverse of taking an object at rest and letting it go, and having it travel at an acceleration of 4.5 miles per hour per second for 10 seconds. So it's going to pick up speed. Right? Oh, 1/2. Jeez. That could have been a disaster. Right, which makes complete sense now. Because if we look at the velocity, this is the this is the derivative of that equation, which would then be 2/2 a times t. So acceleration times time is going to be 4.5 times 10. Uh-oh. No, 4.5 times 10 gets us, we're fine, gets us 45 miles an hour is the velocity. So that's the derivative of this particular equation. So yeah, this makes sense. So s is going to be equal to, again, this is sort of the reverse of what we were doing before. This is going to be 4.5 times 10 squared is 100 times 1/2 is 50. So 5 times 45 is then going to be 180 plus 45 is 225. 225 feet. Oh dear, we're mixing units again. Miles per hour per second. Yeah, we shouldn't have done that. Okay, so instead of 4.5, we'll use 6.6. We'll just make the units better. Okay, so 6.6 times 50 is going to be 330. Oof. So, decelerating from 45 to 0 in 10 seconds, which is not that fast these days, but nonetheless, is going to take a total of 330 feet. So that is a long way on a road. Yeah. All right, that works. We don't need to do that. We can just do it backwards. All right, 1-3. Speedometer of an automobile registers 15 miles an hour at a given instant. And 8 seconds later, it registers 47 miles per hour. What was the rate of acceleration? What was the distance traveled during this interval? Again, same deal. And I didn't say it before, but if anybody needs to raid and run or what have you, feel free. Take care of yourself. Make sure you get your hydration in. This is just water, I promise. We already finished off the beer. Alright, so our rate of acceleration is going to be 47 was our finish, minus 15 over 8 seconds is going to get us a total of 32 miles per hour over 8 seconds is 4 miles per hour per second. And then we multiply this by, again, 3,600 divided by 5280. No, that's the other way around. Wait. 5280, again, this is feet is what we want up top, and 3,600 is what we want on the bottom. 4 times 5280 divided by 3,600 is 5.86, and the 6 is repeat. Feet per second squared. Yep, hope everybody was having a good Halloween. My kids went out with one of our friends from across the street and one of our daughter's friends who is staying the night. Hopefully they're actually asleep by now. It is currently 12:50, so I really hope they're asleep. Otherwise they're gonna have a very rude awakening in the morning. Alright, S is equal to 1/2 a t squared, which is going to be 1/2. A is 5.86 repeated times time was 8 seconds. Alright, so that's going to be 32 times. Okay. So 8 squared is 64, divided by 2 is 32, times 5.86 with the 6's repeat, gets us a total of 187.7 with 3's repeated after, and that is in feet. We are going to then use significant figures to say that the best significant figure we have, I don't know if we should count that as 1 or 2. I would imagine technically that's 1, but 1-3. Oh, no, answers are in the back, right. -3. Nope, 3 significant figures. So this is going to be 5.87 feet per second squared. And 188 feet. Alright, we'll do a couple more here. An elevator starts from rest and gains speed at a rate of 4 feet per second for 2 seconds. Elevator rises at 4 feet per second squared. Over 2 second period. Then it continues to rise at a rate of 8 feet per second. If a person weighing 160 pounds is standing on a spring scale on the elevator, what will the scale read during the first 2 seconds and then after? Okay, person weighing 160 pounds is on a scale. What will the scale read during the first 2 seconds? So this is going to, again, be similar to what we saw earlier. It's going to be heavier than 160 pounds. We'll calculate out what that is in a minute. Again, nope. 1 and 2. I know for a fact that during the time after the first 2 seconds of acceleration, the scale will once again show that this is 160 pounds. Once you've started going at a continuous rate, then it will no longer be accelerating, and so you are just doing your standard acceleration due to gravity, which gives you a weight of 160 pounds. We don't even need to look that up. We could calculate it if we want to, but we're not accelerating. So A is going to be 0 during that time. What will the scale read during the first 2 seconds? So what we're going to have is F equals A times G over W, question mark. F equals A times W over G. All right, other way. It's going to be equal to the acceleration due to gravity. Nope, sorry. Acceleration is... right. 4 feet per second squared. Times their weight is 160 pounds. Divided by g, the acceleration due to gravity felt, is 32.2 feet per second squared. That's feet per second squared and feet per second squared go away, and we just get 4 times 160 is 640. Nope. Divided by 32.2. That is 19.8757 ... pounds of force, which is additional to their normal weight of 160 pounds, which means that this is going to be 160 plus 19.87 pounds is going to be equal to 179.8. 160 pounds, again, if we're just doing 2 significant figures, is going to be 180. 3 significant figures is going to be the same. So we're at 179.87. At least approximately, right? 180 pounds, because we were saying that that was going to be our standard 3 decimal places as significant figures. That's only what was stated in the book. We don't necessarily we don't want to trust that for all of life, but it's good enough for now. Alright, 1.5. Person weighing 160 pounds stood on a spring scale in the elevator. When the elevator started up, the scale momentarily read 182 pounds. When the elevator slowed to a stop, the scale for a short instant read 130 pounds. Find both the acceleration and deceleration of the elevator. Aha. Tricky. Not really. Okay, so acceleration and deceleration. Sure, why not? This is going to be the same equation that we used up here for F equals A times W over G. However, No. G over W times F. Right, this took away 30 pounds, and this one added 22 pounds. Right, 1.5. Good. I did actually label it. I was worried for a second that I didn't. In that, I wasn't that worried. Little late for me to do station identification, but hey, good evening and welcome. My name is Obi-Wan Pez, and this is N Simplex Pachinko. We typically do math streams on Tuesday nights. I was out this week because we were in France. Bonjour, ça va? And just got back on Tuesday. In theory, I could have done another. I could have done a stream on Tuesday, but wasn't feeling it. And then didn't get to do any game streams last week. Well, actually last week because we were out in France as well. The week before that, I didn't do a math stream on Tuesday because our power went out and kept going out multiple times during the day. It was very frustrating. We had to throw away pretty much everything in our fridge. Freezer managed to stay pretty much frozen. Okay. Gravitational acceleration is 32.2. Our weight is 160. And the force was a plus 22. Deceleration is going to be 32.2 over 160 times a negative 30. So technically we can make this a negative acceleration rather than a deceleration, but whatever, it's fine. We can decide precisely what kind of information we'd want to put on there. 32.2 times 22 divided by 160 is going to be 4.4275 feet per second squared. And that is the positive acceleration when we're moving upward, and the deceleration when we are slowing down to reach whatever floor we're trying to reach. 32.2 times negative 30 divided by 160 is going to be a negative 6.0375 feet per second squared. Which again, if we assume is correct to 3 significant figures, this is going to be a plus 4.43 and a minus 6.04 feet per second squared. Okay. If anyone has any more questions, please let me know. I think we're probably going to do some more work out of The Mathematics of Space Exploration by Merle H. Ahrendt next week when we come back on Tuesday. But we will also ask if anybody has any questions, so feel free to do so in the meantime. We might get some use out of this bad boy right here. So we'll figure out, I will figure out what all of the individual bars mean, because I know how to multiply and I know how to divide, but that's about it. There are some really good logarithmic type things that we can use with it. And anyway, we're going to head over to who is live tonight. Alright, we got multiple people playing games tonight. Do we have anybody doing math still? Admiral Stapler. Seed finding, except for math and not Minecraft. Interesting. Irish John is doing Doom 3. Astro Canuck is, as always, doing Lego and brick building until he gets the telescope up. You know, once the light dips enough. Solu is doing Neva, which is an interesting strange game. Maisie is currently doing Phasmophobia and has an awesome outfit. Justice over at Gigglepus Gang is currently playing Silent Breath and has, I don't know what kind of Lee Pace thing he's wearing right now, but you know what? I'm here for it. Cataclysm, as always. Nice outfit. Looks like Michelle Boyd's doing A Quiet Place and has a costume. Ready to Tina has a wild demonic costume and is playing Ayla. Alright, nobody's doing math, so, or, well, we've got one. But you know what? We're going to go see Talos because they are doing Soma tonight. And let me tell you what, Soma is a great game. It is also perfect for Halloween. So if anybody is interested, again, I would also recommend going to go see Admiral_Stapler. Who is currently doing math and again is doing seed finding for some sort of random process. But for right now, we're going to go see Talos and wish him all the best because this is a wild game. If you have not played it, I recommend it. You might want to just duck out. But anyway, I'll see you all on, well, I'll see you all tomorrow because I'll be doing my usual Friday night game stuff. And then we'll hop on over to mathy type stuff next Tuesday. So hope you all have fun. Have a great Halloween. Have a great Dia de los Muertos if you celebrate. And otherwise, we'll see you around. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.